I know I said that we were going to do sound next, but because of some things that were beyond my control, we'll have to talk about light and color, and we'll talk about sound next week. Both of these are various forms of waves. Sound is a mechanical wave. We had talked about that before, that mechanical waves are waves that require a medium to pass through. Light is one of those waves that does not require a medium. It can pass through and travel through a vacuum, and it's part of what's known as the electromagnetic spectrum. The electromagnetic spectrum goes from the long waves, which are things like microwaves and radio waves, to very high energy waves like gamma rays, include things such as X-rays, UV radiation, and visible light. Now, one of the things about light that's sort of interesting is what's known as the duality of light. Light as a particular particle. Albert Einstein actually proposed that light came in packets known as photons. And this was the particle theory of light, that it was a stream of tiny particles that were emitted by a light source. However, light demonstrated many things that were also part of wave phenomena. And so light actually acts both as a wave and as a particle. It travels in straight lines, and it can travel through a vacuum, which most people would think that waves wouldn't be able to do that. It also explains how reflection and refraction work. But then there's the wave theory. Light consists of waves, not particles, actually two transverse waves oscillating at right angles to each other. And what we see here is the concept of diffraction, which is a wave phenomenon and also occurs with light. The wave equation applies to light, where the velocity is equal to 3 times 10 to the 8th. Frequency times wavelength is always equal to this speed. And so there were a lot of people that also thought that light was a wave. And so basically it came to what is known as the dual theory of light. Light is both waves and light is particles. There's something known as the photoelectric effect. The photoelectric effect is the ability of light to knock electrons loose from their orbit. This would be a particle type theory. What is shown in this diagram, by the way, is the wave action of light, where it will diffract around a barrier, and the particle action of light when it is stopped by a barrier. And so sometimes, depending on the situation, you can see one or the other. And this is what makes light unique, and something unique to consider. A photon, as I said before, is a small bundle or packet of energy. So when interacting with matter, photons act like particles, but when traveling through space, photons act like electromagnetic waves. And so this is what is known as the duality theory of light, that light can act as either a wave or a particle. Wave-particle duality. Light has both waves and particles. And you'll read about something known as quantum theory in this regard. Now this is the electromagnetic spectrum. I had mentioned this. You can see on one end of the electromagnetic spectrum on the right is the very long waves, the AM waves, short wave, TV, FM waves. And these all have long waves, low frequency. All of these travel at the speed of light. You can see that the visible spectrum of light is actually a small portion of the electromagnetic spectrum. And then your high energy short waves, things like gamma rays and X-rays. And the reason X-rays can be used is that they are high energy and they will penetrate tissue but not bone, so you can use them to reveal things. So visible light is the part of the electromagnetic spectrum that can be seen or perceived, and the visible spectrum are the 6 colors that can be discerned by the human eye. And on one end you have the blue, purple blue end, the yellow orange in the middle, and then the red on the right side. The three primary colors being blue, yellow, and red, and everything else being a combination of those three primary colors. White light, as we see it, is a mixture of various colors, and black, anything that's black, is the absence of color. So a prism acts on a wave of light. Now this wave has various wavelengths, and the prism slows each of these down in a different amount, and therefore they are refracted a different amount, and they bend a different amount. And what you can see is the shorter waves, the blue waves bend the most, and the longer red bend the least. And then obviously the yellow is in the middle. So a prism separates white light into its component colors by the process of refraction, which we talked about last week. Light, when it passes through glass, slows down, and when it slows down differentially depending on the color. Now, additive primary colors, you'll see various definitions, and there are some definitions that you really need to take note of. And additive primary colors are various combinations of red, green, and blue. And this can create the illusion of almost any color. The combination, you could use combinations of red, green, and blue to create virtually any color that you want to create. So additive is shown on the left here. You have red, green, and blue, and blue plus red, magenta, green plus blue is cyan, and green plus red is yellow. Notice all three together in the middle there gives you white. Subtracted colors, which are the yellow, magenta, and cyan, when they combine, they form the primary colors again, but in the middle you'll see the black instead of white. So subtracted primary colors are illusions of color produced by subtracting certain colors, magenta, cyan, and yellow, from visible light. An additive primary color is always referred to as light, and a subtracted primary color is always referred to as a pigment. Remember that. An additive primary color is always referred to as light. Subtracted primary color is always referred to as a pigment. Yellow, magenta, and cyan, by the way, are frequently used in printers to create the colors that a printer can create. So they are pigments. Now, remember we talked about reflection. And here is an example of reflected light. This is a mirror. A mirror is a surface that reflects light waves and follows the law of reflection, which means the angle of incident is equal to the angle of reflection. A virtual image can be formed by a mirror, and it's an image that appears behind the mirror. So when you look in a mirror, that person looking back at you, which looks like they're behind the mirror and looks just like you, is actually a virtual image. And that means it's not real. It's something you can see, but it's not projected on a screen. A real image is an image that is actually projected on a screen that can be seen. So a real image is formed, and it will be formed in front of the mirror. The virtual image will look like it's behind the mirror. The real image will be in front of the mirror. So if the mirror is in the middle here and the source is coming from the left, if you have an image on the left due to this mirror, then that image is real. If, on the other hand, the image is on the right, as shown in this picture, then that image is virtual. Now, concave and convex mirrors are mirrors that have a certain curvature with relation to the image or to the object. So, for example, on the left is concave because it's curved concave in relation to the object, which is shown an upward arrow. F stands for the focal point of the mirror, And the downward arrow is the image that is formed by the mirror. And you can draw this image based on two primary rays. The first one goes from the top of the upward arrow, reflects off the mirror, passes through the focal point. The second passes to the middle of the mirror and out, and then there's actually a third that can pass through the focal point, hit the mirror, and then reflect back perpendicularly, and it will also strike at the top of the inverted arrow. And I will show you how these are done in class. I can't really show you very well on this. Actually, I think I can. Let me see if I can do that. So here is how these images are drawn. So you have a flat surface and you have a mirror here, and you have a object. Wait, this mirror needs to be concave, sorry. I didn't draw this mirror right, so let me do that again. So here's the surface, and here's the concave mirror, and let's say the focal point is right here. I'm just kind of making this up. You'll have three rays that are drawn. One ray goes directly parallel to the surface and then passes through the focal point. The second passes through the focal point, hits the mirror, and goes directly this way like that, parallel. So the first one goes parallel and then passes through the focal point. The second one passes through the focal point and then goes parallel. And the third one is at the center of the mirror and then comes back out. And all three of these coalesce in one spot where the image is formed. And these are called the three primary rays that form this image. And so that's how this reflection occurs. So as I said, you have spherical mirrors, which are part of a sphere, and the concave mirrors, the reflecting side of the spherical mirror, is on the inside of the sphere, and that means it's toward the image. If the reflecting side is on the outside, then it's curved away as shown on the left, and it's called a convex mirror. The reflecting side of the mirror is on the outside of the sphere. You draw the same three primary rays, but what you end up with, this is a real image on the right, but a virtual image on the left. Now these are lenses, and these take into account the idea of refraction. You see on the left a convex lens, you see on the right a concave lens. And a convex lens bends the light toward the middle at a focal point. A concave lens bends the light away, and the focal point ends up being on the same side as the object itself. So refracted light always bends toward the medium, the normal. That slows it down. And with lenses like this, you're always going from air to glass or some other material that slow it down. So a lens is a piece of glass or other material specifically designed to refract light. So this looks at another aspect of the behavior of light, the refracted behavior of light. And what you have here is, how does a mirage form? Mirages form when light rays from a distant object are reflected in such a way as that they appear closer than they really are. And so what you see down below is a reflected image, and this person is looking at this reflected image. But if he gets to a certain angle, then called the critical angle, then the reflected image will not come out of the water, and it will flatten out, and it appears as though the palm tree disappears. Now also what can happen is something called scintillation. And scintillation is what causes the stars to twinkle, and it's caused by light refraction by passing through various densities of air from outer space to us. And it slows as it comes toward us, and in the process of that, it refracts, and there's interference set up, and that causes the scintillation. A rainbow is also caused by refraction, and it is essentially like putting a prism in the sky. What happens is that white light goes into the water refracts and separates the white light into its various colors. Now, interference also occurs with light, and it can be either a mutual reinforcement or a mutual cancellation. And that's when two or more waves meet, as we talked about before. And what you're looking at here is a process of alternating constructive and destructive interference, making these lines dark, white, dark, white. And it's beyond the scope of this course to explain how that happens, but just know that this picture represents the idea of both constructive and destructive interference. And it looks better at the top part as opposed to the bottom part. It occurs because the thickness of the material changes and changes the angle of refraction, and light rays run into each other, and they either added or subtract from each other when they do that. Iridescence is a term that means that colors which are produced from interference when light is reflected. And so iridescence is a type of color produced that's caused by the interference. Now, shadows are an interesting thing, and shadows show primarily show the process of diffraction. Remember, with diffraction, when a wave hits an object, it bends around the object, and that's what you see with a shadow. Is some of the light passing through, other part does not pass through. So optical diffraction causes the spreading of light rays as the light passes through the obstacle, or past the obstacle. The outside part, where some of the light rays still make it to the surface, is called the penumbra, and it's the lighter part of the shadow. But in the middle of the shadow is the umbra, which is the darker part of the shadow, and it's where light cannot make it, even though it had diffracted around to some extent. Now, this is called double slit diffraction, and what happens with double slit diffraction is alternating areas of interference, positive interference followed by negative interference. And so on the left here, you see the peaks represent positive interference, and the troughs represent negative interference. And as you move out from the middle, the peaks get smaller and smaller, so the amount of constructive interference decreases and the troughs remain in place. So double slit diffraction is diffraction that passes through these narrow slits, and the light fringes that result from constructive interference, so the peaks that are shown here, are called the antinode, and the troughs are called the nodes that are caused by destructive interference. Now, these interferences can also lead to a grating. When you bounce light off a grating, you can also see diffraction that produces color, again for the same reason that color is separated, or white light is separated by diffraction. When you have various levels of interference, you can cause colors to appear. Now, the total electromagnetic spectrum, as I said before, includes radio waves, which are low energy, long wavelength, low frequency. Visible light is sort of in the middle, and then shorter wavelengths, higher frequency, higher energy waves are on the right here. And this just reinforces that idea that you have long wavelength, low energy, low frequency with radio and microwaves, and then short wavelength, high energy, high frequency with X-rays and gamma rays. Radar is when you use these low energy waves, such as microwaves, to detect an object at the distance. It's very much like sonar. You bounce the microwaves off an object, and when it returns, it can tell you this distance, size, and how fast that object is moving. The energy of an electromagnetic wave is directly proportional to its frequency. The energy is equal to Planck's constant times the frequency. Stimulated emission is when a photon is stimulated by its excited electron or excited atoms. And what commonly happens, is you introduce energy in the form of heat frequently into a group of atoms. The energy is absorbed by the atoms, the electrons change their orbit, and then when the energy is removed, when they change orbit, they're called excited. When the energy is removed, the electrons fall back to where they belong, and in the process they emit a photon of energy, and that's called stimulated emission. This just shows some various aspects of specialized light. Specialized light, such as a laser, is a light that's very high energy and it's monochromatic, which means it contains a single spectrum or a single frequency, as opposed to ordinary light, which is a group of spectra. It's coherent, which means the light waves are all in phase with each other, as opposed to white light, which is not coherent. And then lastly, it's directional, which means it's all pointed in one single direction, as opposed to white light, which generally goes in all directions at the same time. By the way, on the slide here, you can see what laser actually means: light amplification by stimulated emission of radiation. So it's a light that's produced by stimulating atoms and then allowing them to produce. It produces a single frequency because the energy is in packets known as quanta, and that energy tells you what frequency of light is generated, and it's all the same. And you can have various types of lasers which will have various colors: red versus green versus blue. We're going to end this by talking just briefly about the speed of light. I did this all in one section because it's not a very long lecture, and talk about the idea of special relativity. The speed of light is always constant and unaffected by the motion of either the source or the receiver. Now that's, you know very well that if you get on a escalator and you start walking up, that your speed is going to be the sum of the amount the escalator is moving and how fast you're climbing the stairs. It'll be the total of those two together. Light is unique in the fact that no matter which direction it's traveling, it can be traveling in the same direction as the Earth, in the opposite direction as the Earth. It always travels at the same speed. It's not affected by motion. And this fact led Einstein to come up with the ideas of general and special relativity, because unlike everything else in the world, light is not affected by the motion of other things. So special relativity states that all motion must be measured relative to some arbitrary reference point. The speed of light is constant in relation to any observer. Now there are some really interesting ideas that come from that we won't talk about because they're very confusing. Actually, we're going to talk about it a little bit, But what you can see here is these things actually don't only matter if you're traveling very quickly or very quickly, that is close to the speed of light. So you have a moving observer and a stationary observer. And if the moving observer is moving at a speed of 1/2 the speed of light, then his clock moves slower than the clock of the stationary observer. The light speed is equal to the distance, and the same light speed occurs in both observers. And so the only way that can happen is for time to be different for these two individuals. And that's known as time dilation. And that's that top equation, is that the time is affected by the speed of if one of the observers is moving close to the speed of light. And it's called time dilation. It makes his clock travel slower than the clock of the person that's sitting still. Another thing that happens is if the person that's moving experiences what's known as length contraction. The length that the experience by the person that's moving is longer than the length experienced by the person that's not moving. Similarly, masses are affected by this phenomenon. So time dilation is the apparent slowing of time for objects traveling at high speeds. You heard about this when you watched the movie Interstellar, that they experienced time dilation when they got close to that one planet, and several years passed on Earth and only a few minutes passed where they were because of the speed they were traveling. The Lorentz contraction, or the length contraction, objects appear shorter in the direction of motion when motion is very rapid. And then lastly, mass increase in objects that are moving very quickly. You just have to remember these three facts. That is that time slows down, lengths appear shorter, and masses increase if you are traveling close to the speed of light. And then general relativity states that gravity is a result of the geometry of space, and is actually gravity is actually affected by, or light is actually affected by gravity and the geometry of space. And this shows that time and light